I want to welcome everybody to the 2018 Charles DeLisi Distinguished Lecture. The Charles DeLisi Distinguished Lecture series celebrates high-impact research and engineering and annually honors one of our faculty or alumni that have had an outstanding record of research and impact in their field. Now, despite the fact that, unfortunately, by mistake, the program doesn't mention Charles DeLisi, which is a major snafu, this speaker series is endowed by a tremendous and wonderful gift by Charles. For those of you, or most of you know of Charles DeLisi, of course, but for those few people here who are not as familiar, Charles was a seminal individual in transforming the College of Engineering from what was primarily an undergraduate engineering school to an extraordinary research intense and research successful College of Engineering. He hired a whole series of senior individuals and junior faculty to transform the reputation of the College of Engineering and started to attract extramural funding, the likes of which we've never seen before, and reputation, the likes of which. He's also an extraordinary figure in the world of the Human Genome Project, being the only person honored by the president for having begun and catalyzed the Human Genome Project. And Charles has also been, of course, a professor of biomedical engineering and have mentored many students and many postdocs in his career. And I want to personally and have all of us thank Charles for his extraordinary impact on the college and his wonderful gift to endow this lecture series. Charles, where are you? Stand up, please. Okay, first, before we get to our honored speaker, at this event, we also announced the winner of the Early Career Excellence Award. This year's winner is Professor Wilson Wang. Wilson, why don't you stand up while I read for about a half an hour? Wilson is the first faculty member from BU to receive both the NIH Director's New Innovator Award and the NSF Career Award, two of the most competitive and prestigious awards for young investigators. He has won close to $5 million in funding from federal agencies. Dr. Wang contributed to the engineering of the first gene metabolic oscillator in E. coli and an artificial cell-cell communication, which is an artificial cell-cell communication device. During his postdoc, he worked on T-cell engineering, which led to his first author paper in Nature. This work continued at Boston University, where he recently became a scientific founder of a new startup company called Senti Biosciences that focuses on creating the next generation of cell-based immunotherapy products. Since coming to BU, he has published new work in Nature Biotechnology, and most recently in the prestigious journal Cell, where he published a paper on engineering genetic circuits in human T cells to tackle tumor heterogeneity. He has built a robust collaborator network, including leading faculty here and BU from all dimensions of synthetic and systems biology. He has 25 publications in or submitted to peer-reviewed journals already that have been cited 1,500 times, 2 book chapters, 3 patents or patents pending, and 34 invited lectures. Wilson, congratulations. Okay, let me introduce our guest speaker, Professor Xin Zhang. Xin got her PhD in mechanical engineering from Hong Kong University of Science and Technology and her postdoc in electrical engineering at MIT. Okay, she is a professor of the mechanical engineering department, the electrical and computer engineering department, the biomedical engineering department, and the division of material science and engineering. Somehow she got left out of the systems engineering division. I don't know how that happened. She's the distinguished professor of engineering. A Boston University's faculty member since 2002, Dr. Zhang leads an interdisciplinary team of researchers focused on fundamental and applied aspects of microelectromechanical systems, or MEMS, and its descendant, NEMS, or micro-nanosystems. Her research group advances basic science of micro and nanomaterials, and then advances technologies for practical applications, ranging from energy to healthcare to homeland security. Her work has been highlighted and or displayed on the cover of journals such as the Journal of Applied Physics, the Journal of Micromechanics and Microengineering, and Science and Nature. Dr. Zhang is a fellow of the AAAS, the American Association for the Advancement of Science. the American Institute for Medical and Biological Engineering, AMB, and ASME, the American Society of Mechanical Engineers, and the IEEE, and the Optical Society, and an Associate Fellow of the American Institute of Aeronautics and Astronautics. She has received numerous awards for research and educational excellence. In 2009, she was named the inaugural Distinguished Faculty Fellow in the College of Engineering, an appointment given to a tenured engineering faculty at Boston University who is on a clear trajectory toward an extraordinary career in all dimensions of science and engineering in 2016. She's clearly fulfilled, it was given to her in 2016, she's clearly fulfilling that trajectory. She was selected as the recipient of the IEEE Sensor Council's Technical Achievement Award in the area of sensors for distinguished contributions to the field of micro-nano electromechanical systems. Dr. Zhang has published over 140 papers in interdisciplinary peer-reviewed journals that have been cited over 9,000 times, and among her 15 PhD students from Boston University, 3 have tenure-track positions at major research institutions like Ohio State and Virginia Tech and UT Austin, and several others are in national laboratories or in high positions in corporations. Xin is the first female full professor in the BU Mechanical Engineering and Photonics Center, and has served as Associate Chair for the Graduate Programs in Mechanical Engineering, and is now Associate Director of Boston University's Nanotechnology Innovation Center, and Director of both the NSF-REU and the NSF-RET sites in integrated nanomanufacturing at Boston University. Today, her talk is titled, That. Please join me in welcoming Professor Xin Zhang.
So I'm not going to read my title. You're going to hear a lot. Hello and welcome, H&W. So this is a photo from Belfast. Indeed stands for Harland and Wolff Company, established in 1861. In early this year, I was in IEEE conference at Belfast for the first time. When I read it, I thought it's a hello and welcome. But NW is a very famous company manufacturing a lot of heavy industry products such as the Titanic. So I went to the museum, it's called Titanic Belfast, opened in 2012. And I saw this article, an article published in Journal of Engineering in 1908, exactly 110 years ago. And then I also feel very connected with the giant turbine in Titanic. Not only the movie Titanic I watched many, many years ago when I was in Hong Kong, but also this shrinked, miniaturized, so-called micro gas turbine engine. We use silicon as the chip and making this 6 millimeter diameter of turbines, and we have a design speed up to 2 million RPM, which is corresponding to 300 to 400 meters per second. So a little background education about myself. I got every possible training degree in engineering. I did my bachelor, master, material science, PhD, mechanical engineering, and then I got my postdoc training mainly on electrical engineering, but joined with aerospace. And then I started my career, some of you may not know, manufacturing engineering. And in 2008, we have this merger of these two departments, manufacturing, aerospace, mechanical. Simply, we call it ME, mechanical engineering. And of course, as Ken said, I'm also delighted to be associated with other departments. And then my major activity is really at the BU Photonics Center. So a lot of you ask me what I do. I said MEMS, microelectromechanical systems. So mainly it's about integration of mechanical elements, sensors, actuators, electronics on a piece of a silicon chip. I can spend 20 minutes on a piece of silicon chip. That's my only materials. And then we use micro-nano fabrication. So when my students, mainly mechanical students, engineering students, ask me what I do, I talk about cars because they feel very connected. And when my friend or family asks me what I do, I talk about phones, because even my grandma has a phone, you know. And then in city Boston, I learned that you have to talk about biology, otherwise you look like an idiot. And so I talk about these skills, and I said I fit in very well. I have a micro-nano, look at the bacteria, cells, all this. I can do a lot of biomedical micro devices. And this is like a conceptual, I just can go on and on. You can think of all kinds of sensors, detectors, and I truly believe the science is just working and compatible. It's going to be a next few decade things. But research-wise, I have this 3-color, which is using MEMS as a platform driven by important application. I think this is about today's gathering, a celebration for society needs. So in the power energy, as I mentioned, before coming to BU, I work on something to the space, gas turbines, combustors, all in micro scales, rocket engines. And then after joining to BU, I go to the downhole, which is oil, gas, all this kind of harsh environment sensors, gas chromatography systems, advanced micro nano manufacturing, and wireless communication, collecting information back. And then in the blue, which is the biomedical part of, I call biomems or bio micro nano systems. So cells or live cells is a perfect unit, not too big, not too small. And then in collaboration with some local hospital, I use heart muscle cell as my unit. And my career was built on optical mechanically, sensing, measuring those tiny piconewton, nanonewton forces, impedance sensing, and fundamentally, we characterize those small-scale viscoelastic polymer materials for the working platform to get a force measurement. And then recent years, in collaboration with local industries such as Draper Lab, hospitals such as BMC, I also involved in some kind of organ-on-chips, functional catheters, or MR contract agents. But today, I will, for the sake of time, just focus on one topic, the theme of my third part of research driven by photonics or optical applications. So I'm not going to talk about physics, but a couple of days ago, I saw the news of a physical review journals are celebrating their 125 years. As we know, there's a lot of fascinating work coming from this journal, Nobel Prize winners. So I quickly get into the website, and I find in early 2000, there's a blueprint from Dr. John Perry and talk about this super lens. So the idea is very simple. You have this slab materials made of a negative refract index material. This kind of material do not exist, so we call metamaterials. I will get into a little bit. So with such kind of artificial material, you can have such kind of phenomena behavior, such as focusing the light. So we call super lensing. And shortly after, people like David Smith at Duke University also demonstrated something big at the microwave range. So what is metamaterials? Just quickly, when we talk about nature material, we talk about atoms, molecules. When we talk about nature properties of materials, we talk about, for example, refract index. Like here, it should be all positive. But when they talk about metamaterials, we talk about their unit, so-called meta atoms. And the unit is super small, much smaller than the working wavelength or frequency. And then you put them in an array fashion in a crystal formats. And then their property lies in their structure, not in their chemical composition. And so with a proper design, at a certain frequency, you could have, for example, index of refraction negative. We call it life-handed materials. So briefly, metamaterials, artificial engineering materials, we can design the property that may not find in the natures, and we can create extraordinary effective microscope behavior by introducing dynamic tuning, dynamic modulation at the material level. So using so-called effective material approach, we can describe such a material, for example, using effective permeability for electromagnetic material, which is the focus of my talk today, and Young's modular Poisson ratio for mechanical, mass density, Bark modulars for acoustic metamaterials. So what are the applications of metamaterial? Why we so care about it? Let me give you two examples. So if you look at the upper, you see this stack of three-dimensional arrays of micro-coil unit cells made of this artificial metamaterial with a negative refract index. Now you have the light coming in, and the light will be refracted not only sharply, but also negatively when it enters such material with a negative refraction. And such phenomena also being preliminary demonstration in labs using experiment, numerical simulation. And in the upper half, there's another interesting, even more fascinating things, so-called invisibility cloaking. So if we will talk about electromagnetic material, we can design their effective permeability with a spatial dispersion, and we can guide the light to bypass this space without touching the object in the middle. So this kind of concept in some movies, such as Harry Potter's Lord of the Rings, and also being demonstrated in labs numerically and experimentally. So this is the layout of my talk. I will use metamaterial as a general term to go over from terahertz infrared to communication to MR imaging. And if I have time, I get into a little bit of acoustics. So let me start with the terahertz. But first of all, I want to say such a material is scalable. So we talk about the beginning of demonstration, the microwave, big, but keep in mind those materials has a unit cells, and from design viewpoint, their property lies in their structure, not their chemical presentation. So you can simply shrink the size of a unit cell, and you can have those materials working at different frequencies from microwave to visible light. So here are some examples. We talk about super lens, a spatial light modulator, perfect absorber, holographic imager. So fascinating extraordinary properties being realized, such as I mentioned, negative refraction, invisible cloaking, and perfect absorption, which I will get into a little bit. So a few words about terahertz. Some of you may know, some of you may not know. So this little blue is between microwave and infrared and visible. So when people talk about microwave, they talk about electronics, for wireless, radar communication application. When people talk about infrared visible, we talk about photonics, and we talk about powerful lasers, LEDs, functional lens for optical fiber applications. So the terahertz refers to this region often being called a terahertz gap. A gap meaning we just don't have many things working in this region. Sources, detectors, modulator, traditional microwave or optical just simply don't work here. So we call it new materials. If we cannot find a new material in nature, we have to find an artificial material such as metamaterials. And then here's the wish list. So the wavelength of 1 terahertz is about 300 micrometers. So metamaterials should be working very well. We talk about high power source, more sensitive, cheaper detectors, and compact way to tune or modulation the radiation. A few words about characterization. Just like an optical tool characterization for nature material, we can use FTIR, UV visible spectroscopy. But we use a system called Terahertz TDS, which stands for Time Domain Spectroscopy, mainly because it gives us both amplitude and also the phase response of metamaterial. So this is the base. It could be more complicated, depends on application. But simply you have this phantom second laser pulse to you, optical crystal to generate this terahertz radiation, and you focus the terahertz onto your sample, and you measure the response in time domain, and you transfer this to the frequency domain. So in your right, you can see the transmission as a function frequency within time domain, and using Fourier transform, you can get its frequency domain. And then the dashed line indicates a minimal transmission happens at the resonance frequency. Application, I talk about metamaterial application. What about terahertz? Another fascinating thing to get into it. So terahertz radiation is safe to use on humans, which is very, very important. Can penetrate many visibly opaque materials such as clothing, the newspapers, cardboard, wood, plastic, ceramics, and be reflected by metals. So you see the knife hiding inside the newspaper. So it's very useful to safety scanning. And importantly, we can do this simultaneous investigation for both physical and chemical properties of materials. And in recent years, people also talk about some potential promising application for cancer imaging, such as skin cancers. So this is the layout of my work, I use a cover image from my group. But mainly, as I said, MEMS is my engineering platform. On top of that, I integrate metamaterials. For this case, is really electromagnetic metamaterials, and together finding application at the different working frequencies, from 3D manufacturing to nonlinear physics to sensitive chemical sensor detector. And in parallel, we can tune our metamaterials for real-time modulation. So when we started, we numerically simulate our structure, just like many projects, you have to do some design. So here's a dozen unit cell design. As I said, those unit cells tiny, small, much smaller than working wavelengths. And we use FDTD, so-called finite difference time domain. So we can put a dozen of them, and then we can use a photolithography, just spray and pattern it very easily, forming this sheet of unit cells. And then this red showing the polarization. We can polarize it to excite our resonance of the resonating. And those metamaterial made of 200 nanometer of gold, highly transmitting semiconductor substrates such as gallium oxide. And then in your right-hand side, you can see, for example, using number 5 as an example, you can see numerically, we see the electrical field, current density, and experimentally, as I mentioned, using terahertz TDS, you can see the transmission response as a function of frequency. And then furthermore, you can extract the effective parameters such as effective permeability from the spectrum. And then we get into say, well, wait, we can do a lot because it's about design. And so from beginning, we simply can incorporate more than one subunit metamaterial into one unit of a metamaterial cell, and each subunit corresponds to its own resonance mode, and the overall metamaterial preserve those different electromagnetic properties of each subunit, so together they can achieve this kind of multiple resonance of the metamaterial response. So we call wallpaper metamaterials, but nature is more creative. When they highlight our work, they say metamaterial person carpents. So I put a real carpet backgrounds, hoping in the future we can manufacture those electromagnetic metamaterial carpets. So something not necessarily limited by the 2D, a piece of silicon, you can make it stand up in most three-dimensional fashion. Why three-dimensional? Because while you're in the three-dimensional, you don't have that kind of coupling electromagnetic, you can have a pure magnetic response. So I call it stand-up magnetic metamaterials. So without further details, we have those electroplating you can do in your kitchen, that kind of changing color for colors. So we can electroplate those multi-layer unit cells, array of them. So this is a real picture we take after fabrication, not only on rigid substrate, but also on flexible. So my student holding a piece of films with those array for structure. So now you can get something phenomenally interesting because you can study the pure magnetic. So now it's permeability as a function of frequency, and you see something becoming negative, exhibiting this Lorentz-like response. So basically, I'm a big fan of manufacturing in small scale, make a micro heat engine. Since then, I think I can make anything. So this is a metamaterial on all kinds of substrates you can imagine. Ultra thin, only 400 nanometer as compared to 500 micrometers of silicon wafer, and then you can concentrate this electric field, and you can make your metamaterial super sensitive to this dielectric environment change, make it a very good chemical sensor. In collaboration with Tufts University, we learned silk is a very interesting, promising material. So for our case, we can spray our metamaterial to those pre-made silk films, and then we can make this entirely happen in a dry, chemical-free environment so as to minimize any possible contamination, so as to maintain the integrity and the biocompatibility for various applications. And people, including this college, many colleagues talk about cost-effective, practical, portable, disposable diagnostic devices for on-site detection towards global healthcare, environmental monitoring, water, food safety, and medical reduction. So for this case, we can use low-cost materials such as paper and spray level metamaterial, and this is the demonstration of a low-cost glucose sensor with metamaterial array. And then, as I said, metamaterial can be on flexible substrate, so we can make it on any kinds, from polymer to metals to semiconductors for all kinds of application. And the thickness could be only 5 micrometer in thickness, and we can wrap them into a cylinder with a few diameter forming a sheet. And you can see the red and blue before and after this wrapping forming. You don't really see much difference. And this is probably the first functional terahertz wave sensing with our electromagnetic metamaterials developed by our group. As I said, MEMS is my working platform. So my MEMS, very simple, is cantilevers. Everybody know cantilevers. And it's a biomaterial cantilever made of 2 materials, nitride and gold. So people use this kind all the time, array of them, and you can use it, the so-called focal planar array for detection, for imaging, for sensing. So I use my cantilever array as a platform, and this cantilever can absorb the absorption radiation and convert to the heat, and this heat will induce the thermal mismatch and can bend the cantilever for sensing and detection. So that's basically how it works. But we integrate with metamaterial, and metamaterial for this case as the absorbing material, see before, after. So we have this significant enhancement on radiation absorption, increasing sensitivity, responsivity, so we can demonstrate at a different frequency, mainly at the terahertz. And then science putting this airport security picture in their article, highlight our paper saying smaller sensor on the way, metamaterials to see in terahertz. And then in recent years funded by DoD, we further push it to smaller scale. Now you see those metamaterial absorbing units much, much smaller, so you can push it for infrared camera applications. And then I talk about sensor. Now I want to switch the gear a little bit. Similar thing, absorber. So absorbers, so we talk about absorber, metamaterial absorber, or metamaterial perfect absorber. Of course, nothing works perfectly. But when we talk about perfect, meaning it can absorb all of the electro and magnetic radiation without any reflection, without any transmission, without any scattering. So for the microwave military, you can think of this radar cross-section reduction, so you can have the stealth coating with metamaterials for security application. Infravisible, we talk about bolometers, cameras, detectors, and also energy harvesting, make something super black. And then fundamentally, I'm in the BU Photonics Center, such a nonlinear absorber also has tremendous application in ultrafast physics for sensor eye protection. So we started, and our most famous paper published with collaborations probably this terahertz perfect absorber. So I won't get you too bored, but it's very simple. 2 layers of metamaterial, 1 layer we call E metamaterial, like this, and the other is just like a cut wire. And in between, you put some spacer material, and together you put on some kind of a substrate. So together we call tri-layer metamaterial absorber, and then we use some kind of theory called the effective meaning theory. Of course, I won't get into that, but simply the top layer can tailor permittivity epsilon, and the coupling between top and bottom metamaterial can control the permittivity. So you basically together can match this impedance of the absorber to free space, to unit. You can reach some perfect absorption. So both science and nature highlight our work, filling the terahertz gap near perfect black. And furthermore, we can push it to highly flexible, only 15 micrometer in thickness, working at both electromagnetic with a wide range of angle, at every possible angle operation with terahertz. And then you can, such a cool fun part of design problem, you can tailor the top layer 1 + 1 = 2. You can make it dual band, triple band, multi-band. And the important thing, all those peaks can be independently tailored and optimized, providing tremendous flexibility. So my group has been working on this absorber for quite some years because we are fascinated by such a mathematically complex problem. We like difficult problem, but we also like important problem. It has a lot of applications. So theoretically, based on interference theory, we have this intrinsic model to give you the toolbox. You want an absorber, you have this input, have that output, here's your thickness layer, here's your materials. And fabrication-wise, we make, again, 3-dimensional. So this time is all metal, truly 3-dimensional. So you have a high Qs, high quality factor. So you have this super sensitivity of functions. And application-wise, we can wrap those flexible absorber to metallic cylinders. And the design frequency, you can see here, you have a near 400-fold reduction of those radar cross sections. So it's a lot of tremendous application for defense. So now further switch gear, I talk about sensors, I talk about absorbers. Now I talk about something more dynamic, actuators, something moving, something in motion. So again, I talk about cantilevers. So this cantilever, again, bilayers, array format. But this time, instead of using it as a sensing platform, I use it as a tuning platform. So moving. So those cantilever array MEMS platform, when you thermal annihilate at a different temperature, different time, and they will bend. Because these two materials dislike each other, they will bend with a different curvature. So you have those pre-fixed curvature array being configured, and then we integrate the metamaterials. And then under different configuration, for example, magnetic resonance, electroresonance, so you can just plot this beautiful curve, finding the transmission as a function of frequency under all possible configuration. So this is probably one of the first mechanically, structurally reconfigurable, tunable metamaterials. I mean, mechanical engineering, I did my PhD in solid mechanics, so I call it a stress engineering. So you take a bunch of stress and doing a lot of interesting things. But I have to be honest, this structure is being frozen from the beginning, and you do a lot of measurement. It's not real-time tuning. So let me show you something real-time in recent years by my group. So this is a cover image showing real-time, but pay attention to here. So those are finger type of structures, so-called comb drives. Another textbook kind of actuation system from MEMS. You can easily find it. You can have a beautiful precision manufacturing, and people use it all the time for actuation of a structure. So with that, now you see two chips. One chip is movable, and the other chip is fixed. So the movable chip, you have an array of metamaterials supported by those folded beams, and then comb drive actuator. So those actuators will move you metamaterials, and lower is array of metamaterial on fixed beams. So one chip is relative moving to the other chip, you have this coupling of two layers, and you can have the modulation of the metamaterial. So this is the basic idea. And then I will just use one slide to tell you fabrication, because it's important in micro nano scale, different color, different material. For the movable layer, you have this film-coated substrate. You pattern it, you deposit electron, you pattern the metamaterial, you deep etching those actuation supporting beam, and you etch through the whole structure, make it a freestanding. And then the other layer just just fixed. You have metamaterial pattern, you etch through, and then you bond these two layers together with some kind of adhesive layer using aligner bonders. So this is structure you can see under the microscope, the movable metamaterial layers, supporting beams, a comb drive actuation, and the top showing before after this ladder shift, and lower show the bonded devices ready for lab demonstration. The gap between these two layers is probably 10 to 15 micrometers, and the spacing between those unit cells is about 50 micrometers. So let me show you something experimentally demonstrating the transmission response of metamaterial by tuning this transmission. So you can see the transmission as a function of frequency along with the phase as a function of frequency. So when these two layers align, no voltage applied, you can see the two peaks. So we use some kind of a model theory, so-called couple model theory. I won't get into detail. In the lower frequency is symmetric, higher frequency is anti-symmetric. You basically see these two shapes, one is aligned. So now let me show you this animation. Now you apply the voltage, you actuate your comb drives, and you laterally shift these two layers relative to each other. And you can see this merging of these two resonance modes leading to the modulation on the transmission amplitude and the transmission phase. So we can fine-tuning those ladder shape by applying different voltage, and we can generate this 2D color map of the transmission amplitude, and this is real-time video showing real-time transmission amplitude modulation. And then not only without further details, as another video shows here, the function of our devices is not limited by the amplitude of modulation. It can be also for the phase modulation, and we can derive those group delay for metamaterial from the phase response. So it's a real-time tunable group delay with a phase modulation. In the upper left, you can see those group delay all negative near the resonance with a small ladder shift and becoming positive for larger ladder shift. And in red, you can see this temporal response of the group delay. For the red color is aligned negative group delay. For green color is misaligned with a positive group delay. I always ask myself why, what's the application? Simply you can use it for terahertz equalizer in optics, photonics, for terahertz power synthesis. Another cover image show you the second example super quickly. So now you see the cantilever again. So cantilever, for this case, we use so-called surface micromachining techniques. So we fabricate those cantilever array on top of our surface with a tiny gap. Again, different color, different materials. So you have this green nitride film coated deposit pattern for connection. And you have this blue aluminum deposit making contact with the substrates. And then you put this yellow of gold for the bottom electrons, wires. And then pay attention to this pink material, polyimide, we call it a spacer layer or sacrificial layer, meaning this is the gap between your cantilever, and we need it temporarily. We will get rid of it later. And then you have this copper metamaterial cantilever array, and then you remove all the pink polyimide. So now your cantilever flying on top of your substrates. So now this is how it looks like after fabrication. But when you zoom in, you see the cantilever, you see the pad, you see the small gap. So simply, without further detail of physics, I can tell you this kind of cantilever, because of its configuration, it behaves differently around X and Y direction. So around X direction is a second order resonator, around Y is a first order high pass filter. So when you actuate the cantilever by applying voltage, you change the gap, you change the capacitance, you can reconfigure only the Y polarization instead of X. And you can plot this data, which is both transmission and the phase as a function of frequency under different voltage, along with current and electric field distribution. So probably this transmission map can give you much better idea. So you apply voltage, you put on the cantilever, you change the gap, you change the effective capacitance, and you shift this resonant frequency, give you a number. If you apply 40 DC voltage, you have about 230 gigahertz of a shift. And then, so this I will click twice, so you can see both videos. So the above below it shows you this electric field distribution in the transmission region at the design frequency. So basically, as I said, the nature difference along X and Y direction in cantilever just enabled us this polarization conversion, which is very important. So it simply works as a quarter wave play. So when no voltage applied, you have this metamaterial, you have a linear to circular. When you apply the voltage, you have linear to linear. So this table, to conclude, the cantilever just gave you all kinds of options you have different incident angle, different working design frequency under different voltage. You can scale it to other frequency regime. So let's read quickly the first. 18 degree, 0.93 terahertz, no voltage applied, right-handed. And then you gradually increase the voltage, it becoming linearly and left-handed polarized. So meaning that we can not only control over the amplitude phase, but also the polarization. So quickly summarize my first part. It's terahertz infrared. I show you some chemical sensor detectors. We use metamaterial to enhance the sensing. I show you some absorbers. So we use metamaterial to tailor the absorption. And then we use a comb drive actuator to control the tunability to modulate amplitude, phase, and the group delay. And then we use a cantilever to control the frequency modulation, and then over phase, amplitude, and polarization. So when my student asks me what is metamaterial, so from engineering practice, I think there's no clear borderline between materials and devices. So it's a very useful toolbox from engineering and science. You have many, many options, even just using the same geometry to play with. And many people, including myself, believe that we're one step closer to real-world application. So I want to entertain a little bit to talk about broader, better application, starting from wireless communication. Again, I will use metamaterial. So the idea is that since 2010, I was luckily funded by a host of oil gas industry. Since then, every time I put gas in my car, I pay attention to who they are. I want to get to know them better, so they gave me more money. So this is a general idea. They put a lot of sensors in the downhole environments. And those sensors got to be miniaturized because the fracture of downhole is very, very small. So those sensors are micron scales, few micrometers, few tens of micrometers, and then you collect those sensors back to the surface, you read those information, get the information. So for this case, the information is their power. We talk about real oil, gas, energy. The more information get, the more efficiency they can have production-wise. But I'm not the sensor team. I'm the only team funded by them since 2010 on communication. So the platform I work is a wireless charging and communication platform. We can handle large number of sensors of that microchip. They simultaneously with high efficiencies. And those chips, for demonstration, to give you the idea, they're very small. It's double layer antenna with a side length less than 1 millimeter, and with RFID chip. Many of you know RFID. And then this is general idea how it works. I'm away from the micron scale. So if we read from your right to your left, so we start with this tube, which is the oil gas template. Is a polycarbonate tube with a microchip flowing inside. And then you see this 1, 2, 3 part, which is my communication platform. The first part is the coupling loop, and the second coil. Together, they form this magnetically coupled reader antenna. And the second is metamaterial. I'll get into a little bit. It's 10 millimeter in diameter, much bigger, array of them, and then deployed in the cross section of a second coil. And further to your left is this little green with a resonator helix on the surface, so-called a local field enhancement package. When you further zoom in, you can see these microchips less than 1 millimeter in the side length, and then hosted by this green local field enhancement package. And this package carrying the chip travels through this polycarbonate tubes, and the information is stored in the memory, will be retrieved when the sensor, the chip passing through the reader antenna. So the working frequency for this case about 1 gigahertz. So thanks for their funding for so long time. So this is the roadmap of our communication distance in the unit of millimeters near field as a function of time. To be honest, in the beginning, I was quite struggled with a sub-millimeter. And then with this package, 3 parts of a communication platform, we were able to make breakthrough from few millimeter to a few tens millimeter to up to 100 micrometers. So when they talk about 100 micrometers, I use international unit, it's 4 inches. When they told me in the beginning, I almost passed out, but now we can reach that distance. But I can tell you, metamaterial play one of the important role, not the only important role. But I want to talk about metamaterial. So this case, metamaterial is array of helix spiral structure is a second order resonator, and its diameter is 10 millimeter, much bigger than the metamaterial I showed you before, but its working wavelength is at microwaves. So still significantly smaller than the working wavelength. So design-wise, it's just the same or similar kind of engineering practice, lots of fun. You can design those material to interact with a radar antenna by resonance to generate this magnetic field enhancement at the cross-section metamaterial, and you can enhance the communication. So this is the platform we build not only for lab demonstration. When we work with industry, they want something delivered for field test. So as I said, you have this 100 millimeter diameter of the tube you build. You have one fitting port, and divided this chamber divided by 4 individual channels and made of antenna array, and each of them has those array of metamaterials, and the channel is 50 millimeter in diameter, metamaterial is 10 millimeter in diameter. And then I want to say this kind of system, you can use it to boost the transfer coefficients for wireless charging communications, and we can push to 4 inches. But it's not limited for oil gas. Now we can apply to many scenarios. For example, another funded work, we start to do this so-called through glass reading. So inside this glass, they build this chamber. It's super harsh environment. They want to mimic the harsh environment. They have pH sensor, pressure sensor, temperature sensor, but they want to get the information out. So we'll be able to do this kind of harsh environment modeling and monitor. And even more excitingly, we can collaborate with some real hospital doing some animals, human being implantable devices for wireless communication. And I want to talk about something even more exciting and even more recently about MRI. Everybody know MRI, right? Magnetic resonance imaging, which represents a cornerstone of the diagnostic tools available in modern healthcare. As we're talking market size of more than 5 billion, it's going to go 7 billion. Why? Aging population, MR compatible, pacemakers becoming available, MR in emerging markets in Asia, in Africa. So this market is tremendous. So this work is in collaboration with BU Radiology. Steve Anderson, who's in the hospital, cannot make it today. So when Steve and I met, he told me the most important thing is SNR. Take it, signal to noise ratio. This is the fundamental performance matrix of MRI from a radiology viewpoint. And then we know, MR system just go ever increasing static field, 1.5T, 3T, 7T, all associated with increasing cost. The system becoming more and more complex, lots of safety concerns. And then our first project was not that exciting, to be honest. We kind of micro-nano those particles, size, shape, specific particle, so-called contract agents. And we published paper. We demonstrate some useful applications. But we all agree that the administration of those contract agents, you have to inject it. When you improve the SNR, you also have some safety concerns. People start talking about some redeposition, those metal in your brains, So I don't talk about too much but now you see metamaterials here. So now you see this schematic, under this patient, not in addition to the surface coil, we have this carbon of a metamaterial. We can even entirely replacing the surface coil, just have this carbon metamaterials. And this metamaterial, same or similar, is magnetic metamaterial, yielding RF amplification, improving our SNR during the imaging. So when Steve and I work on that, he always said, keep in mind, when you have SNR increase, it equals to 3 things. The improving efficiency, decrease time or cost, and increase resolution and quality. When I look at it, it's always about quality of image, but the decrease time and decrease cost is also significantly important from practical reason. So there's some relatively mature technology. People talk about advanced RF coils, post-synthesis, data acquisition techniques, and I have to be humble, honest here. I think metamaterial approach is not replacing anything, is addictive to a host of other working technology. And as always, more is better. So how they look? Very similar. We saw terahertz array. Now it just get bigger. But it's okay. It works at megahertz. Your unit cell is still smaller than your working frequency. It's an array of a helic structure. They couple each other. They have a bark resonance. And as a good design engineering, you have those frequency to match your working frequency of the MRI. Now you can boost the magnetic imaging for both transmission, reception phase to enhance the SNR. So without further detail, let me show you preliminary prototyping. We actually use a chip printer printing those metamaterial scaffold. We use copper, another cheap material, wound our metallic wire around those metamaterial scaffold. So this is how MR Metamaterial look like. And you put a array of them, and you build a customer phantom. And this is a picture taken from my lab before going to radiology department. And then you can see this phantom validation without metamaterial, with metamaterial, and when you near the metamaterial, you see this boosting of imaging. And when you draw this dashed line gradually away from this metamaterial, it decaying, of course. So you can draw this SNR improvement ratio as a function of distance. Without any optimization, without any precision part of manufacturing, we can easily get 4 or 5 times enhancement. And then now we're working on, of course, and we always want to get optimization, precision. But Steve tell me, wait, the most important thing is about clinical application. So we are tailoring our engineering platform for spine, for breast, for brain, for knees, for all kinds of applications. It's just a lot of fun. So I will keep you updated. So I want to entitle title this slide to conclude to see or not to see. So at the beginning, I have this perfect lens blueprint from Dr. Perry, and many people follow his work, has this super lens, breaking diffraction limit, improving resolution. I also show you our work, the imager detector see better, see something we cannot see before, and we have this RMR improvement, not only see better, and also decrease your cost, decrease the time. But drawing a line, you can also make something not to see. We have this invisible cloaking, the cloaking in transmission mode, the cloaking in reflection mode. You can make this super black, reduce this radar cross-section for defense application. So I'm an engineer and big fan of design. So by tailoring, manipulating these waves and fields using this artificial material, your design is essentially allow you to functionalize your artificial material driven by many important applications. Last 2 minutes, I promise, acoustic metamaterials. So this time is to hear, or not to hear. So it's relatively new, not only for my group, it's for the entire world. I truly encourage you to get into this field. It's fascinating. People talk about this kind of material structure can modulate, can shape the sound. So I give you some conceptual image. For example, you can have a broadcasting sound in the public area targeting specific location, a specific person. When you drive your car long distance, you really want to have the driver from passenger simultaneously listen to different music. When you watch TV, your wife probably only wants you to listen to TV and without interference with others. You can also have this selective announcement in the public area. I can go on like forever. There are lots of interesting things. But thanks for the quality student, great collaboration. So just early this week, we published work, our first project in Nature Communication. You're welcome to discuss more, but I will tell you the first project is we have this numerical analytical base of the model, and we can simultaneously modulate transmission phase and the transmission amplitude. So you see the lower image, we can have this beam focusing, steering using our metamaterials. And then during the review process, they said, wow, you have to get some experimental. So we print this a meta surface, and then in the local regime, we can demonstrate some successful simultaneous modulation of a phase and a modulation. So there's 2 other projects. So another metamaterial, you see metamaterial kind of buried in this. And if you look at this structure, your immediate impression is, wow, it's so open, right? It's ultra open structure to filter the sound in a specific frequency. The reason it's open is that if you think of, for example, the cooling fan noise, super loud in a very narrow band, but you also need to leave the fan open, right? So that's the general idea of a metamaterial, and we are in the lab demonstration. Another thing is, I put the BU logo here, is the tunability. Similar to electromagnetic, you really want to have the surface tunable for phase modulation. You want to mimic the functionality of the phase array transducer from far source. And this, I can tell you, is going to be a lot of biomedical clinical applications. So this is the layout. I talk about metamaterial for various reasons, for various applications, and not only in the phases design, but also get into applications society need. I think that's the mission of engineering. I'd like to conclude my talk to thank all the funding agencies, all my students. So this is the recent picture we take at the BU Photonics Center. I want to say everything made at BU, proudly made at BU Photonics Center. And then here's the past current student, PhD, postdoc, master, undergrad, high school student, teachers, tremendous. And then, as Ken said, three of them moved to major university as a faculty, Ohio State, UT Austin, Virginia Tech. Many of them back to Asia as professors. And I can read a long list of local industry in US and national lab from Apple, Aramco, Draper, GE, Livermore, Merck, MGH, Lincoln, and many, many others. And then I have a long list of collaborators. I'm deeply grateful for their support over the past decade, but I don't have room to list them all here, but I have to mention these two gentlemen. So in your lab is Professor Rick Avery. We have more than a decade of collaboration. He's now at the UC San Diego, and our work is mainly on Terahertz Metamaterials. And then the middle is Dr. Steve Anderson. He's MD. I call him true doctor. He's at the radiology. I also call him my super postdoc. He always spends some time with me. And we recent work on MRI imaging and acoustic metamaterial is even more promising. Everybody know this gentleman, Tom Bufano. I like this picture because it shows a typical him, always busy, always on the phone, but he always has a few minutes for me. I'm lucky to have him as a mentor. So this is a book I bought right after I accepted a faculty position at BU. I was nervous. I don't know how to write proposals. I had never seen proposal in my life, you know. And then I believe it or not, I never even finished reading this book because I have a good colleague, good staff support, and then my mentor, Tom Bufano. And then Boston is my only city in US. And I love Boston every aspect, and I'm a big fan of sports. And we're lucky to be alive here because we have a greatest team in the world, right? Celtics, Bruins, both in the playoffs. I have to go home to watch their playoffs tonight, right? Good luck. And then Red Sox. I used nothing about baseball. I had to write proposals, so many long hours. So the Red Sox is perfect because you can mute the song, you can be with them, you can go deep night, right? And then they have a refreshed season now, and I wish them the best. And of course, my forever topic, my most favorite, New England Patriots. So I think I learned a lot about leadership, knowledge retention, many. And I think research is a sport, is a team sport, right? And I really want to dedicate this talk to my students. They are the force of my research. They spend endless hours in labs. And they basically take ownership from beginning on every possible problem. Some problem is wrong from beginning, but they just own it and they prove me wrong. And with all the dedication, hard working, and they motivating me, they pushing me to higher level, motivating me to do better. So I want to thank everybody here. I want to thank BU Engineering. I want to thank Boston University. Thank you very much.
Everybody take a breath. Wow. We have time for a few questions for Xin. Right over here. We have a microphone. Please don't ask your question until you have the microphone, and don't sing.
Hello, Professor Zhang. I have a question for you. After you design the acoustic metamaterial, can it be used in all wavelengths? Like if you just simply scale down or scale up the structure?
So I will have this, the answer is yes. As Reza, could you stand up? And then Jacob stands up. So the first two authors is my dedicated PhD student and the undergrad student, Jacob, mechanical engineering. You know, I have 3 Jacobs in my lab. So the key recipe is you have to work with Jacob. And then Reza, could you answer a question?
Yes, so we basically in the microphone. Yes, so we basically in the design process target specific frequency range, but it's scalable. So you can scale the structure and use it for the range of the frequency that you want.
Okay, thank you.
Other questions from the audience? I would like to ask a question about the MRI materials. Looked like the amplification was only about 2 centimeters of the entire phantom, which for MRI, obviously, you want to see more deeply than that. What's the likelihood you can get much deeper into the individual for clinical applications?
So, you know, we can go deeper from optimization, precision viewpoint, and also even the surface. There's already some kind of application for spines. But Guangwu, could you stand up, answer this question? So he's the key player on this, and talk about the depths with our future plan.
Okay, so the answer is yes, that we can achieve deeper penetration of the signal. And briefly talking is that the penetration depth is related to the design of the unit cell. So we can do optimizations of that unit cell to achieve more depth. And the result we show in this presentation is just the preliminary design. We are working on it, and we already can see the twice or third, 3 times increase of the penetration depth by doing the simulation and the measurement.
So Ken, I have to tell you, this project was funded by Dean's Catalyst Award initially, and followed by Coulter and Ignatian, but they're after you. So thank you so much.
Oh, mine too? Time for one more question, if there is any. Okay, so before we go to the reception, I'd like to, first of all, who has the microphone? I need a microphone because I'm going to walk away from here. Can we bring out? So to honor Xin as the DeLisi Distinguished Lecturer, we've endowed a wooden chair, which has her name on it.
Nice.
And as the 2011 Distinguished Lecturer, Charles DeLisi Distinguished Lecturer, and we've framed the announcement of the talk, which we'll put outside the Dean's office, of course, as well. So please join me again in thanking and awarding Xin the hand that she needs for this wonderful, wonderful body of work. Thank you.
Thank you so much.